Alrighty, so let's get going again. I hope you enjoy your lunch and you come back ready for more dynamic programming. From now on, we're going to briefly review what optimality means. We're going to define optimality. And then we're going to state the standard optimality results. And then once we get there, we can get on to the fun stuff of looking at algorithms and comparing them, seeing how they work and implementing them and running them and seeing which ones are fast and which ones are not so fast and talking about why and so on. All right, so we got to this point here. I was making a little analogy here with geometric series. So if A is a number strictly less than 1, sorry, it's dark and a bit hard to see, but maybe you can see this. Some of these guys is equal to 1 and 1 minus A. If A is a matrix where all the eigenvalues are less than 1 in modulus, this is R of A. R of A means the spectral radius of A, which is the max of the absolute value or the modulus of the eigenvalues. Less than 1, then sum AT, this is the T, summing over T from 0 onwards, AT is equal to identity minus A inverse. Can't read that, can you? Okay. Anyway, excuse me. Yeah. Yeah. Oh, yeah. It sounded weird. Okay. I hope I didn't deafen anyone. Yeah. So let's try and do this right. Anyway, so that was, if you're struggling with this equality here, it's just saying that, you know, think of this guy as a matrix, and this geometric sum of the powers of the matrix under weak conditions that are satisfied here, the conditions that are satisfied here, is equal to the identity minus this guy inverse. That's the standard result. That's all that means. John Ross was talking just before lunch about the Robert Lucas quote from his famous asset pricing paper, where he was saying that a little geometric series goes a long way, which was a very, very modest way of describing his contribution to asset pricing. But it's definitely increased. So this is the basic geometric series result that we're using here, and you can see that this is going to help us if we want to compute lifetime value. Lifetime value of being policy. If we think about computing this guy, this is the lifetime value of following policy statement. If I think about computing this guy, it seems like that would be pretty easy. We could MATLAB or Python or Julia or whatever you like. And that's true, but it does get problematic when the number of elements in the state space is large. So if your state space contains 1 million elements, which you can easily do once you have a bunch of state variables, as you probably discovered, these things, the size of the state space expand exponentially in the dimensions. That's the curse of dimensionality. Then we can get into a situation where we have many, many states. And if we have many states, for example, 1 million states, then the size of this matrix is 1 million by 1 million. And if you have a matrix that big, it's hard to store in memory, let alone invert it. So what might we do in that situation? Well, maybe we can take an iterative approach to computing this guy. So for that purpose, let's introduce what's called a policy operator. So some of you will have seen this guy before. And I've written it 2 different ways. I've written it element by element at the top of the slide. And I've written it towards the bottom of the slide in vector notation. So fixing a policy sigma, I take V. When I apply this operator, T sub sigma of V is going to be, yeah, I should point to the mouse if we call it zoom. Is going to be reward, you know, this is a reward function condition I'm using the policy sigma. This is a dynamics when we use the policy sigma. It's similar to the Bellman operator, except with the Bellman operator, we take the max. But I'm not going to take the max. I'm just fix the policy and just see what happens with this particular policy. Okay, so this operator here, it's not hard to convince yourself. Well, a couple of things. One is that it's a contraction. And the proof is super easy, but we don't really need to go through all the steps now. You can come back and have a look if you're interested. But it's all I'm using there. If you broke that down element by elements, you would see it's basically just more. Okay, so all of these guys are contractions of modulus data. That means they all have unique fixed points. So theta sigma, then using a T sigma, T sigma has a unique fixed point. What is that fixed point? Well, it's just a beta of sigma. It's the lifetime value of that policy. So just so we don't get confused here, actually, then we're going to expand this, you can see. So remember that B sub sigma is the lifetime value of forwarding policy sigma, which is equal to this value. Now, if B is a fixed point of T sub sigma, that's to say that B satisfies this equation, which is if I rearrange it, so that B satisfies this equation, which says that B is exactly this sigma. So what we've done is we've introduced an operator such that the fixed points of this operator are exactly the lifetime values for any choice of sigma. And we know that it only has one fixed point. And we know that it's contraction. So now this gives me another way to compute the lifetime values, which are these B sub sigmas. These are the guys I want to compute. I can compute them like this. But sometimes that's hard, or sometimes I want to think about doing it a different way. So what I can say is I take this operator and pick any of these and apply it and apply it and apply it and keep going. And I'm going to generate a sequence of these, which is just arrays on my computer. And they're going to converge to the lifetime value. Any questions on that? So that gives us another way to compute the sigma, to compute the lifetime values. And that could be handy when we don't want to invert a really large matrix. And it might also be handy if we don't want to compute V sub sigma exactly, but we want an approximation, because computing it exactly is too expensive. And we're going to look at an algorithm just like that pretty soon. I'm just going to share this one. Right there. Okay, so just a little bit more terminology that we've seen before. I'm going to call a policy greedy, B greedy, if it satisfies this for every X. What's that saying? This is exactly the same idea as before. I'm going to take B. I'm going to think of it like the value function. And I'm going to compute my policy accordingly. And if B is the value function, that's going to give me the exact optimal policy. And so I think of B, which is values the next period states. That turns my problem, my infinite horizon problem, into a two-period problem. If I have exactly the right values, that'll give me an optimal policy. But maybe B is not exactly B star, and maybe it'll give me something close. Anyway, for any B that you give me, this is the definition of a B greedy policy. It treats B like the value. Bellman's equation we've already seen, the Bellman operator, but the definition is analogous to what we had before. We introduced this operator T, such that fixed points of this operator T, of the Bellman operator, exactly coincide with solutions to Bellman's equation. You saw that in your search. This is just the general version of that. It's just a way to help us find things that satisfy Bellman's equation. Find these that satisfy Bellman's equation, which we happen to know are equal to value functions, which give us optimal policies. Now, just playing around with the definitions here. This is an equivalent way to say that sigma is V greedy. And maybe it's a little bit tedious because it's just a matter of definitions. But this is going to help me in a second because I want to explain the algorithms that we use geometrically. So this is just a little observation that if I take a policy sigma that's V greedy, that says that it satisfies that definition of V greedy, which says that if we use that policy, we attain the maximum on the right-hand side of the Bellman equation, i.e. we attain the value that the Bellman operator had given us. Just a little observation that greedy policies, V greedy policies should satisfy and V. If I change V to W, yeah, okay, it's not true anymore, but at V is true. Okay, so basically the way it works is the Bellman operator. One way to think about it, the Bellman operator, we've got all these policy operators. Give me a policy, let's say my policy is sigma prime. And now I've got an operator corresponding to sigma prime, that's my policy operator. And T is the upper envelope of these guys. T is the one that takes the max. This is a very loose visualization, right? In fact, we're working in high dimensional spaces. But if we collapsed everything down to one dimension, this is what the picture would look like. The Bellman operator is the upper envelope of the policy operators. If I pick an arbitrary policy at B, it's going to be less than P of B. If I pick the greedy one, it's going to be exactly on B. So visually, the situation was something like this. Okay, the Bellman operator is a contraction. We've already talked about that. You can prove it in many different ways. There's one proof there, but let's skip it. This is a well-known fact. Let's quickly remind ourselves of the definition. The value function is the maximum of the lifetime values. So before, like I said, when I first started studying dynamic programming, I felt really insecure because I didn't know what things meant. I didn't know what expectations meant, and I didn't know what value functions meant. But if we look at it in this way, it's now super concrete. The value function at X is the maximal value we can get to look at all of the policies. So like I said, now in reinforcement learning, some people are just searching, just doing hill climbing in policy space. They just take this and then they take policy and they search through D sigma, looking at different policies, trying to do hill climbing up to the maximum. With a big neural network that just smooths everything out. So we're gonna try and find the optimal policy a little bit more systematically. But anyway, now we've got the value function defined very clearly, and we can say a policy is optimal if it attains the value function. The policy is optimal exactly when it produces maximal value. The policy is optimal if it's the guy that maximizes here for all X. So let's look at it like this. Again, collapsing things down to one dimension. We've got lifetime values, and the value function is the upper envelope of the lifetime values. Now, in the way that I've drawn this, there's no optimal policy. Remember the definition of an optimal policy. A policy is optimal if it's equal to the value function everywhere. Now I've got a lifetime value of this policy, sigma prime prime, and here's another lifetime value. And then the value function is the upper envelope, the max of these, but it's not equal to either of them. But for MDPs, we know that optimal policies always exist. So this is not possible. there's going to be some guy, one of these black lines, lifetime value, that lies above all of them. Well, that's one of the fundamental results. So here's the fundamental result of optimality for Markov decision processes. So take our Markov decision process and then take our value function as best defined and the Bellman operator. And in this setting, we know that V star, the value function, is the unique fixed point of V. And therefore, it's the unique solution of Bellman's equation. And a feasible policy is optimal if and only if it's V star green. So this is just slightly fancy way of saying things that you already know. And I'm not trying to be fancy for fancy's sake. I'm just trying to get it clear because I want to play around with different ideas and algorithms. Think about different ways of computing things and getting clear about what we do. Okay, so that's the basic fundamental results of dynamic programming in this standard setup of decision processes. There's the proof there. If you want to read it, it's all there. It's only like 5 slides and it's really straightforward. If you get the urge to step through the proof of this fundamental theorem, I think you'll find in these couple of slides. So I think that was important to confusing people. In those couple of slides, you'll see that this is a very straightforward arguments that lead us to this fundamental result. Just basically dates back originally. Any questions at this stage? Yeah.
Sigma belongs to the big sigma set. Big sigma is an action thing.
Yeah. So thank you for reminding me, because I tend to skip over notation pretty quickly. So a policy is a map from states to actions. So it's a function from X to A. And then we have the notion of the feasible policies. So they're the ones that respect the constraint equated by gamma. This is how feasibility corresponds to the body constraints. And the set of all feasible policies is capital T. So when we maximize, it's just a maximization problem. We've got this set, capital sigma, and now we just need to search it for the guy that gives us the highest value. That's all we're doing. Now, if we could differentiate things, then we might try and set, that the objective function differentiated, set that to 0, try and do gradient ascent, something like that. In this setting, though, everything is discrete. And we're looking for a systematic way to try and find the guy that gives us the highest.
So in the graph you had before, where you had T of yes, this one. So there is an optimal policy, just follow sigma line up to the crossing point and then follow
So this one, yeah, so in this situation, we've got the state variables. I'm kind of, really simplifying things to present it visually, but X is just one dimensional here, so it could be like the wage in the job search problem. And then we choose a particular policy, and for each policy we choose, we get the value we can get from every state. So this, if I pick this policy sigma prime, these are the values I can get from the different states. If I start off here, I'm going to get this lifetime value. If I start off here, I'm going to get this lifetime value. So the lifetime value of any given policy is always going to be a function of the state because it depends on where we start. Okay. And then I'm looking for the function that's biggest out of all of these black ones. So V star is just a construct. How we find that? Yeah. Absolutely, yeah. So this is I'm trying to give you a realistic picture. In real dynamic programming problems that we solve, these segments can be huge. Absolutely. But then I would get bored of drawing all of these lines on the graph, so I just put it in.
Is it always exists?
Sorry?
Is it always?
Yeah, so it's a really good question, right? Does there always exist one that dominates them all? Is there always going to be some sigma that gives me a V sigma that's bigger than all of these guys? And the answer is yes, for Markov decision processes. And it follows, so this is a statement for India. There's always going to be an optimal policy. Given the structure of the problem that we've just set up, there's always going to be a V sigma that's bigger than all of these guys.
There could also be multiple policies.
Yeah, because we haven't assumed something like strict concavity that would give us unique maximizers. So there could be ties. There could be ties. But 3 actually follows easily from 2. Right? A feasible policy is optimal if and only if it's V star greedy. Well, V star is a well-defined thing. And then given V star, I can certainly take a V star greedy policy. And now I've got an optimal policy. So fact 3 follows easily from fact 2. So fact 1 and fact 2 are the deep things. But the provability is not that hard to get there. And it's kind of beautiful. So if you'd like to go through it, I encourage you to do it. But I'm more inclined to go into algorithms. Any more questions? Okay, so let's talk a bit about algorithms. And the algorithm that we've met so far is value function iteration. Now I'm going to introduce the 2 other probably most important algorithms besides value function iteration. These are called Howard policy iteration and optimistic policy iteration. The names vary a little bit in the literature. This is terminology is relatively the same. Okay, so value function iteration we know. Value function iteration is I'm going to pick an initial guess, and then I'm going to iterate with t, apply t again, and go round and round, right, until, let's say, the distance between this guy and the next guy is small enough. So this iterative process is slowing down. Okay? And then stop and take that guy. Think of that as a good approximation of V star. And then take the greedy policy and we're done. So that's value function iteration. Any questions on that?
That's going to be an arbitrary threshold.
It is going to be an arbitrary threshold, absolutely.
And is there any guarantee that it actually slows down?
That's right. So the question is, that's I'm just repeating for the Zoom audience. The question is this threshold epsilon in some sense arbitrary, and we have guarantees about good performance yet? And the answer is yes, we do. We can determine, once we know epsilon, once we set epsilon in the algorithm, from that we can back out an upper bound on the error introduced by the approximation. Now I haven't included it here, but it is in the textbook. And the one that I've included is pretty standard. It's also a pretty pessimistic bound. But people don't use them much in practice, these theoretical bounds, because the performance tends to be a lot better than this kind of like worst case bound. But basically, because everything's a contraction here, we get nice stable performance that allows us to compute these kind of bounds and guarantee good performance. Time complexity. So I won't go into time complexity, but the rate of convergence is what's called the linear rate of convergence. Let me come back to that when I compare it to other algorithms. But thanks for the question. So value function iteration is globally convergent. We've seen that it's robust. You can start anywhere and iterate with T, and you get a good approximation to V star. And once you've got this good approximation, you can just treat it like the value function, take the greedy policy, and you're going to get something that's very close to. It's also very easy to implement, easy to understand. Very popular. Okay, so now let's talk about two other algorithms. And these two other algorithms are sometimes significantly faster than value function iteration, but not always. And it is very hardware dependent, it's problem dependent, it's software dependent, and it's hardware dependent. And so we'll look at some different timings and some implementations, and then at the end, we'll talk a bit about why we see good performance in some situations. At least to the extent of my knowledge, and then maybe people like Bellman and Bellman will have good insights as well. Okay, so the first one is sometimes just called policy iteration, and sometimes called Howard policy iteration. When economists talk about policy iteration, they sometimes think about iterating on Euler equations, and which is actually isomorphic to value function iteration, so I don't want to talk about that. I'm thinking about a particular algorithm that goes like this. It's very simple. I'm going to pick an initial policy. Then I get the lifetime value of that policy. Once I've got that lifetime value, I take the greedy policy with respect to that value. So if you like, I'm taking this guy, compute the lifetime value of sigma, and now from that guy, I take the greedy policy. I treat that like the value function. And get a policy. Now I've got a new policy. I get the lifetime value of that policy. And then I get the greedy policy. Lifetime value, greedy policy, lifetime value. So we iterate. So a lot of modern artificial intelligence literature is using some variation on this kind of method. Now, why does it converge and what sort of properties does it have? So this is just the same thing written algorithmically, but I'm not sure it adds anything to the this way. It's just saying exactly the same thing. So let me see this. Okay, let's go to a picture. Okay, so here's a picture where I've condensed everything down to one dimension again. And sorry, what was your name? Yura? So Yura was unhappy because I didn't have enough policies. So now, and I think the comment's fair enough because that was a wild simplification that I gave you in that picture. And this is also a big simplification. But in this picture, I'm going to let you think that there's a whole lot of policies now. And so because there's all these different policies, and hence all these different lines here, the policy operators, the upper envelope of these guys, which is the Bellman operator, as we know, is going to be more like a smooth curve now. And when we do value function iteration, we take this curve, this is P, and I just start somewhere, this is value space, this is the V. I collapse everything down to one dimension. And we just, there's a 45-degree diagram, right? We go backwards and forwards. Forget about the orange line. Just think about the blue one and the 45-degree line. We just iterate towards the fixed one. That's value function iteration. So what we do with Howard policy iteration is we take a sigma and we take the value of that. This is the value space, so this is the V sigma. And now I take the greedy policy. Now what's the greedy policy? The greedy policy, which I call sigma prime, remember we had this characterization of greedy policy? So to say that sigma prime is greedy at V sigma is the same thing as saying that it's, when you use that sigma prime at this point, it's the same as using the Bellman operator. We had that a few slides back. So it's where T sigma prime, so it is T sigma prime and T are equal. So I'm going to take that guy. I'm going to take this sigma prime, and then I'm going to solve out for its lifetime value. So to do that, I take the fixed one of this T operator, T sigma operator, T sigma prime operator. Just take the fixed one. Remember that the lifetime values are the fixed points of these operators. So what I've done is I've taken this tangent line and I've taken the fixed point of the tangent line. And now I'm going to repeat that process. So I'm solving for the fixed point of that blue line, which is the fixed point of T, which is the value function, the thing that I want. I'm doing it by taking these tangent lines, which are linear approximations, take their fixed points, and then repeat. Now, this might remind you of algorithms that you use for root finding. And the algorithm in question, or at least one I'm thinking of, is called Newton's method. So when we solve for zeros of a function, we take the tangent function, the linear tangent function, and find the zero of that, and then take that as our next guess and repeat. And we can do that for fixed points as well, and it looks exactly like this. So Howard policy iteration is exactly analogous to Newton's method.
There's a question online, which maybe you can come back to this point. What is the difference between the value iteration and Howard policy iteration? Maybe in this picture?
Yeah. So the value function iteration in this picture, ignore the orange line. Just look at the blue line. The dashed line is a 45-degree line. And we all know that if let's say I pick a point B here and iterate. And if you've used a 45-degree diagram before, you'll know that my iterates are going to go here and here and here and here and here and here and here, and I'll converge to the fixed point. So that's value function iteration. Howard policy iteration, I'm going to take the tangent lines, solve for their fixed points. So I'm basically taking the gradient. I'm using the gradient information, jumping to the fixed point of that gradient, and repeating the process. So this is akin to Newton's Newton iteration, or the Newton-Raphson method, it's sometimes called. And the Newton-Raphson method is known to have a faster rate of convergence than standard fixed point iteration, value function iteration. So let me be a little bit clear with my terminology. If I just pick a point and start iterating with T, that's the value function iteration. It's also called, in general, if we think about an arbitrary function, it's also called successive approximation. Take a guess. I apply the function, I get a new guess. I apply the function, I get a new guess. And we go around. So that successive approximation for computing fixed points in general has a linear rate of convergence. Newton-Raphson method has what's called a quadratic rate of convergence. And that can make a massive difference, those different rates. I'm not going to go into the further details of mathematics, but it's all in the textbook if you're interested in further detail. So any questions at this point? Yes, yeah. So in the present setting, I skipped over that, so thank you for reminding me. So the question was, does this always converge to a unique solution? The answer is yes. Well, okay, so let me be a little bit clearer. In the setting that we're studying, there's no guarantee that the optimal policy is unique because we don't have concavity or something like that. So there could be ties. There could be equally optimal policies. But if we don't really care about breaking these ties very much, what we know is that this algorithm always converges to an exact optimal policy in a finite number of steps. So that's quite a nice result, right? Because I don't know if you've used Newton's method to compute zeros of functions, so Newton wraps them, and sometimes it goes pretty crazy. I can see some people nodding. But in this situation, even though this is akin to Newton, it's globally converged with exact optimal. Given our finite state and action space. Basically, the value always keeps going up, strictly. And then that can't happen forever. And so when it stops, we've got an optimal policy. The set of policies is finite.
And is this anyhow sensitive to Jessup? Because Newton must be very sensitive to Jessup.
So I guess one answer is completely insensitive in the sense that if you take any feasible policies, it will converge, which is kind of remarkable. Given that it's in Newton. But again, if you have a clever guess, something that's probably close to the optimal policy, it's going to converge fast. Any other questions or comments on this? So I'm going to introduce one other algorithm. And the other algorithm, I can go through all the mathematical details, but it's easier just to look at this picture. And the other one's just a small variation on Newton. And the idea is this. Maybe computing the exact fixed point is expensive. I've got this linear function, and in higher dimensions, it's going to be a linear system. And I need to solve it for the fixed point, which is just the lifetime value of that policy. So we talked about situations where the state space might have a million elements, and now we need to invert matrices that are a million by a million. That could be a problem. And another issue is, look, we're trying to get an approximation for the optimal policy. Do we really need to compute the exact fixed point of the policy operators exactly? Do I exactly need to get this guy before I go to the next step? What if I just got something close to this guy and then went to the next step? So to get something close to the fixed point, what I could do is I could just iterate with this operator that's represented by the orange line. This is the fixed point, this is the 45-degree diagram. I'm just going to apply it a few times. Boom, 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 boom. Converging towards the fixed point. Might not exactly get there, but that's okay. And then I go to the next step. I compute the green policy. And then we get a new tangent line. And then we do it again. So that's called optimistic policy iteration. So with optimistic policy iteration, we have a parameter now, which is the number of times that we iterate seeking the fixed point. I'm going to denote that by m. So if m is infinity in the limits, I'm going to get the exact fixed point, and I'm back to Howard. And actually, if m is equal to 1, I'm just doing value function iteration. It's in the slides, and it's easy to see if you look at the slides, but if I just take one step, look at these functions that we put here. So if I just take one step, it's the same taking one step using the orange line and the blue line. So one step, if m is equal to 1, I'm back to value function iteration. If m is equal to infinity, I get to Howard policy iteration. So this in-between guy, which I'm calling optimistic policy iteration, understand it, is some convex combination, if you like, of the other two algorithms. If you like to see it more algorithmically, it looks like that. Okay, so is there any questions or comments on these three different algorithms? Yeah. What is not V greedy? So I guess pick the V, which we can think of as something like a yes of the value function. And then if we treated that guy like the value function and we optimize that policy, we get the greedy policy. A non-greedy policy is anything else, any other policy. What does it look like? It's almost completely unconstrained, right? We've got this whole big set of policies. The V greedy one is one specific one. In terms of the picture here, I guess we have lines, this would be the upper envelope of a whole lot of lines. So there might be another line that comes down here like this, for example, and touches P here. Okay. And then in this picture, a non-greedy policy might give you an operator that's tangent to T somewhere else. I don't know if that helps or doesn't help. I mean, these pictures help to some degree. We're shrinking it down to just one-dimensional problem. Reality is high-dimensional. But hopefully this gives you some feeling for what the algorithms are and why they work. Any other questions? Yeah.
There is one thing that confusing me. So you're saying that that's divided the upper envelope of a bunch of policies. So what happens to the existence of a single policy that is above all of them?
So yeah, so the picture is hard. I had to stare at this myself a long time. So this is not so much the upper envelope as a collection of policies, as it is for each policy. So I've taken a sigma prime, it says it's a greedy policy with respect to this guy. And then this line here, the orange line, is the operator corresponding to that policy. And so what T is it's the upper envelope of all of these operators. Yeah.
Honesty and value consideration, you do it every time. However, you do it once you reach this point. And I guess the question for me is when do we choose to do this capital greedy policies?
Yeah, so the answer is that, yeah, so basically the question is, do we want to, when we compare these two algorithms, we've got trade-offs. In one of them, I'm computing a whole lot of greedy policies. In others, I have to solve for the fixed point of the operators, right? If I do Howard, I need to solve for these exact fixed points. And in high dimensions, I'm inverting a linear system. So do I want to be computing a whole lot of little optimization steps, which is value function iteration? Or with Howard policy iteration, I'm going to be solving linear systems, which are potentially high dimensional, but I probably don't have to do it as often. The Howard policy iteration, like I said, it converges faster. So I don't need to, so they tend to be big steps, computationally expensive steps, but there's fewer of them. Now, which is better? That's super dependent on the hardware that we're going to look at. And what I'm going to argue when I show you some implementations is that increasingly what we want to do is something like Howard policy iteration, where we do a few big steps rather than a whole lot of tiny steps. And the reason is that when we do a few big steps, it's easier to parallelize the problem. If I have to do a whole lot of little steps like this, to go from here to here and there to there and there to there, it's a very sequential problem. And it's hard for me to run this in parallel. If I have to solve a few big steps, then I can look at each step and figure out how to do it in parallel efficiently. So the more that we use parallel architectures, things like GPUs, hardware accelerators, the more attractive things like Howard policy integration become. And so I'll show you, we'll run through that live, hopefully, and we'll see that in action, and then we'll talk about it again. It's a good question. Yeah.
I think one point to add is that computing the V3D policy is very simple, right? It's like a Bellman equation without a max. You just take the utility plus the discounted value.
Yeah, so computing a greedy policy, I guess what Peter was saying, computing a greedy policy is actually pretty cheap. It doesn't take long.
The fixed point.
Yeah. But again, so yeah, so if you have to do it a lot, even though it's a little thing, if you're doing a lot of those steps, it can be computationally expensive. It tends to be fairly sequential and non-parallel.
Yeah, another thing, I'm going to talk about this later, in illustrating a different context. The rate of conversion of self-approximation depends on beta or the discount factor. Intuitively, you're trying to calculate the infinite sum of a very long future where the far future matters and beta is supposed to be 1. And in that case, it's a self-approximation where value function iteration not going to be effective, and the Howard is going to be very powerful because rate of conversion there does not depend on beta.
Yeah, so that's a really good point. So I guess if we look at that geometrically, if beta is really close to 1, then these policy operators are going to have slopes very close to 1. And the T, everything's going to have slope really close to 1. Because basically, T is going to run along the 45-degree line and take a long time to touch it. And if you iterate like that, you're going to take ages to get there. And in that situation, it's going to be more effective to use something like Howard. Okay, so I've got 2 remaining topics. Are there any more questions on the algorithms? So I've got 2 remaining things I want to do. It's fine, go ahead, like an hour or something. Maybe less. 50 minutes? 40 minutes. Okay, I'm going to get myself into trouble here. So one thing I want to do is talk about something that we talked about at the start, which is look at job search. And we saw how we could take this job search problem, which was like, we were looking at value functions, which would be vectors, and then we collapsed it. You're just looking at continuation values, which were just numbers. And so we reduced the dimensionality of the problem. So that's one thing we want to talk about. We want to talk about it a bit more systematically, and I definitely want to get there. And we want to talk about how those ideas can interact with things like policy iteration, for example. Maybe we could collapse the dimensionality of the problem, and at the same time, we could switch from value function iteration to Howard policy iteration. So we get 2 steps of 2 additional levels of efficiency. So we want to be able to mix these things together. That's one thing I want to talk about. The other thing I want to talk about is actually implementing this stuff on computers. And since you guys have done so well providing a whole lot of notation and theory and some graphs that are a little bit hard to interpret, why don't we take a break from theory now and we'll look at the implementation. So let's actually compute some of this stuff and see the algorithms running. Without going into too many of the details, we'll just have a quick overview of seeing this stuff in action. And then let's come back at the end and do a little bit more theory where we'll talk about this idea of reducing dimensionality, or what I call refactoring dynamic programs. So to do this, what I'm going to do is I'm going to try and run stuff live. Trying to run stuff live in seminars like this is always a relatively good disaster. Things that work really well right up until that point always go wrong. But I'm going to run it on Google Colab, and Google Colab is pretty reliable actually. I haven't had too many problems with it, I have to say. The Colab, if you have a Google account, you can follow along with what I'm going to do. All you need to do is go to colab.research.google.com and sign in with your Google account. and sign in your Google account. And then you can copy what I do. Now, having said that, you can see that I've got a little pro badge there. And that means that I'm paying $10 US a month to Google. And the deal is that if I pay that to Google, Google promises that they'll give me priority when they allocate hardware. So they don't promise what kind of hardware I'm getting. So I assume that at Google, they've got a whole lot of dusty machines lying in the corner that they're not using anymore. And they've hooked them up, and they've got like really old ones and not so old ones. And if you pay them $10 a month, when you make a connection, they give you one of the ones that's not so old. So we'll see how we go with that. Okay, so the way I'm going to get connected, so let's see if it actually works. I'm going to open a notebook, so I hit open. And then from here, I'm going to go to GitHub. And JStack is my repo, but I want to get on come, so. Hit enter. And now I get all the Pointstone repositories, and here I'm going to scroll down to the one that I introduced you to at the start of my call, which is DSE workshop. And I'll see a collection of notebooks here. So I'm going to pick out a couple of these notebooks. The first one, I've got job search, so we could go over that, but it's not super exciting. So let's do something a little bit more interesting. I'm going to pick out optimal savings. And so this is a really basic optimal, infinite horizon optimal savings problem. And the idea is that W is going to be wealth, and C is consumption, and Y is labor income. Capital R is a gross interest rate. And I'm going to have a Bellman equation, and the right-hand side of the Bellman equation is going to look something like that. So basically, I want to get the right value function. How's the font size, guys? Do you want something bigger, or is that big? A little bigger? Everyone happy? Who's not happy? Everyone's happy. Okay, so let's what we need to do is just write down the right-hand side of the Bellman equation. And once we've got that, then we've got our policy operators and our Bellman operator just by maximizing it. And then we're going to do value function iteration, and we're going to do other things and see how we go. All right, to execute cells, I do shift enter. I know that, okay, I need to connect. Let's just be out here. So let's get a code cell here. If you want this to run, you actually need to say pip install once econ. Shift enter. It's going to complain about something that I'm not going to care about because I'm only going to blow up Google servers on my own. So worry about the warning messages. I'm just installing the Pointstone library. And at this point, you can see that it's initializing. So now it's connecting me to some kind of machine. And my library is installed. And now I write my code. Now the code that I write, I'm not going to go into a lot of detail about it. I'm more just going to describe it at a high level. You can see that I've got a function here for successive approximation. So with this function, I would pass in a function or an operator if you like, which I've denoted by T, and an initial guess. And all that's going to happen is I'm just going to iterate on this guy. It's like value function iteration. I set X to my initial guess. I update, get the new guy. I look at the distance. That's my error. If the error is too big, I keep going. And I keep iterating. So this successive approximation is the basic fixed point iteration. So that's not very exciting. So let's not worry about that. I'm going to define a model And the way that I set it up is I'm gonna pack everything into a little object called a tuple, but let's not worry about the details. This is just organization. This is where I'm getting down to business here. So this is the unmaximized right-hand side of the Bellman equation. So the problem, like I said, it's an optimal savings problem. Utility is going to be CRA utility. So I've got a choice of current wealth. I take as given current wealth and current labor income, and I'm going to choose next period's wealth, which is effectively choosing how much I save and how much I consume. And then I get utility from consumption. And then this is discounted continuation value, given the current guess of the value function. Now, this little NG here, does anyone know what that's doing? Yeah, that's right. This is telling Python that I want this guy to be just-in-time compiled. So I'm just-in-time compiling it with a library called number. And that essentially means that this function, when it gets executed the first time, the instructions inside the function is going to be compiled down to machine code as a whole. And that machine code, given that this is a very simple set of operations, I'm just taking exponents and multiplying things and subtracting things, it's going to compile this down very efficiently. So the execution speed of this when it's just-in-time compiled will be the same as something like Fortran. So highly optimized C or Fortran, but basically as fast as you can go when you're running an assembly. So after I've done that, I'm going to introduce a policy operator. And the policy operator is just going to be, I've got a given policy. And when I put that policy in the right-hand side of the Bellman equation, that's applying the policy operator. That's applying T sigma. So that's very easy to implement. And T is just maxing. I'm just taking the max instead. Remember, B is the right-hand side of the Bellman equation. I'm going to define these various operators. And you can see that in each case, I'm using this little NJ thing here. So I'm compiling this down to very fast machine code. And you can also say that parallel equals true. So I'm saying that I want this for loop to be parallelized. So when I compute the value of following a policy, I'm going to compute it at each different state, each different x, and that job is going to be parallelized. And the parallelization is going to happen on the CPU. And I'm kind of manually specifying here exactly how I want that parallelization to occur. This little P range here is saying parallel range. So I'm saying I want this stuff parallelized and telling me how to be done. And then I'm going to execute these functions. I have a field that yes. Okay, and then all right, so how would policy iteration is a little bit trickier, and I'm not going to go through the details of this, but in fact, I don't think I've really written this very nicely. So ignoring the details, what I'm doing here is I'm setting up, increase the font size a bit. At the end of the day, I'm computing V sub sigma. Okay? And to do that, I needed to invert this matrix. This is exactly our definition of V sub sigma, the lifetime values. And to do that, I need to set up the matrices properly, which is a little bit fiddly, so that's the messy stuff that you've got there. And then this linear.solve is applying a standard solve for linear systems, which is coming out of the NumPy library, which falls back into something like LaHark, which is very efficient. Very linear systems. So and now from here, defining things like value iteration or Howard policy iteration is very straightforward. And for value function iteration, I'm just going to apply successive approximation. That's 6-point iteration to the Bellman operator T. Let's not worry about all the little details here. That's happening. With Howard, if you look at Howard, what I'm going to do is I'm going to get the value. I'm going to have a policy in mind. I'm going to get the value of that policy. I'm going to get the greedy policy. And if I haven't converged yet, I'll go around again. So that's exactly what we were talking about before. Okay, so tests. Optimistic policy iteration means I'm just going to iterate with a policy operator instead. And I'm going to iterate n times. Similar to Howard, but with that approximation. Okay, so now we can test and see how long these take to run. So to make it a bit more interesting, let's insist that we print out some messages that we go wrong. Okay, and solvers, good, test, good. And let's try value function iteration and see how that goes. So we've started value function iteration. Now this is an optimal saving problem. And in this problem, the grid size, the number of elements of the state, so the grid size is like 100 by 150, so 15,000 grid elements. And we can see that value function is ticking away. I can monitor this a little bit. I'll get this up, for example. There's another there, but it's installable. Yeah.
Is that up desk yet?
Maybe it's just, I think you can just do it out these days. You're right.
Time of all situations. Installed, yeah, up to get installed.
You're right. Thank you. Will we do value function iteration? We will. Each one. Okay, so you can see that Google has generously given me exactly 2 CPUs. And the 2 CPUs are working pretty hard, around about 90%. So I've got a bit of parallelization going on, but not an awful lot. And also, because I've manually parallelized this, you can guarantee that I haven't done the best job possible in terms of how much speed this speed out is. I'm sure that my attempt at parallelization is suboptimal. So we terminated successfully in 554 iterations, and it took us 142 seconds. So that's, reasonably fast. It's not terrible. In general, Python is known as a slow language, but once we incorporate it with the scientific libraries, it can be very fast. And like I said, that's running at around about the speed that you expect something that's really in Fortran to run. With a little bit of parallelization on top. But we've only got 2 CPUs, so not a great deal. Okay, so let's see if we can do something a little bit better. So 142 seconds. Okay, so now we'll do something that I've been playing around with and Phil's been playing around with as well. This is a library called JAX, which has come out recently. Well, a couple of years ago. So the other algorithms, the Howard policy iteration takes a little bit longer in this context, in this setting. And optimistic policy iteration. I showed a picture of the times. So for the optimal savings, problem looks something like this. So here is time taken. This was on a different machine, and this machine had a lot more CPUs. And the amount of time that it took to run the value function iteration was a bit over 8 seconds, maybe 9 seconds. Howard policy iteration was down around 1 second. This axis here is M. So M is the parameter of optimistic policy iteration. And what we find is that for a lot of intermediate values of M, optimistic policy iteration is going to be the fastest of all of these algorithms. So I have to caution you here that this result is very dependent on the problem that you're looking at. And it's also very dependent on the hardware that you're using, as I'll try and show you in just a second. But I suppose the take-home message from this is that at least we know that value function iteration is not necessarily the fastest algorithm. We may want to think about using something like Howard. Howard can be fiddly to implement and sometimes problematic in very high dimensions. And in that setting, we might think instead about optimistic policy iteration, which is very, very simple to implement and often very well there. Okay, so let's go back to implementation. I'm trying to do something this time. I'll go through that again. Using a library called Google JAX. How many people here have used Google JAX before? Yeah, so not many people. Google JAX is something that the Google people have been working away on for a few years, and they released it about 2 years ago. And it's originally designed for deep learning and optimizing parameters in neural networks. But unlike some of the earlier libraries that they released, like TensorFlow, in this case, they released some of the building blocks. And these building blocks do things like linear algebra and computing derivatives and so on. And they have the neat trick, the library has the neat trick of looking for a hardware accelerator like a GPU in the system. And if it detects it, it's going to generate specialized machine code for that particular hardware. And it's going to do that very transparently. If it doesn't detect it, it's going to optimize for the CPU instead. So let's try now connecting again. Let's see. Let's install the point online again. Okay, so this is now connecting and it's giving me an instance, and by default, it's going to give me an instance that doesn't have a GPU. But I want to have a GPU in this case. So I can pick what I want. I can have a GPU or a CPU. So let's go ahead and grab the GPU and let's be greedy and let's get the premium one. And let's see what Google's going to give us. So now it has to initialize again. Now I have to install the library. Yes. Okay. Okay, and I can see this that the active we're going to be connected. Yes, we've got a GPU, and I think this one, I'm by no means a hardware expert, but I think this is a pretty nice commercial grade GPU that we've been given with. 40 gigabytes of RAM. I don't know how many cores this thing has, but I guess it's around about 8,000 cores. So on my laptop, I have 8 cores, it has about 8,000 cores. Okay, so let's set this running. We need to change the code a little bit. And I'm not going to go through the details, but I'm happy to chat with people about it afterwards. But the basic idea with JAX is that you need to vectorize your code. So anyone who's written anything with MATLAB, NumPy, is going to be very familiar with this idea of trying to get rid of loops. Put everything in vectorized operations. And that is going to allow JAX to see the whole operation, and it's actually what it's going to do is going to, in addition to that, look at, so if I write functions, let me show you later on. So these functions look similar to what we had before, but I just wrote them without loops to make everything vectorized. And at this point, you can see I'm doing this, calling this jax.git. And what I'm saying is that I want these functions to be just-in-time compiled, but now they're being just-in-time compiled by JAX. And what JAX does is essentially look at what we want to send into the GPU, and it tries to fuse all of those operations together and do them in the most efficient way. So rather than sending bits and pieces to the GPU, which is expensive, you can look at the whole operation, figure out the most efficient way to do it, and it's all fused together, and then send it out to the GPU and bring it back. Okay, so it's all exactly the same. Let's see what it is. Okay, so let's start with Howard policy duration. I'm going to look at the value function duration on the CPU for 142 seconds. Okay, and that's Howard policy duration, and it took us 1.8 seconds. So that's a big speed gain. And actually, some of that time was taken by just-in-time compilation. So if I do it again, it's now 0.04 seconds. So you remember you saw value function iteration taking away how long it took. And now we can solve the whole problem in 0.04 a second. So massive, massive speed gain from sending this to the GPU. I'm going to run out of time because I still need to cover factory Bellman equations, otherwise Taylor's going to get angry at me. But so that was a very high level look at different ways to implement these programs and different platforms we can use. And I suppose one of the messages that I wanted to convey here is that which algorithm is going to be the most efficient is going to depend on the hardware platform. So here's value function iteration, that's also pretty fast. But it's significantly slower than Howard policy iteration. Yeah, depending on the problem, you're going to get these different speed gains. But basically, the more that we try and push things to GPUs and other accelerators, the more we want to exploit parallelization, which is really the only game in town in terms of trying to get out more efficiency. The more we want to think about algorithms that are not too sequential, but rather do fewer, bigger operations. And that's why we see very big speed gains, particularly for things like Howard policy iteration. Any questions or comments on what I've done? Yeah.
Can anybody get a GPU and play with this? Google.
Anyone can get a GPU. So anyone can play with it on Google Colab. Like I said, if you don't pay for Pro, they might give you a slightly shabbier GPU, and maybe it's significantly slower. So that's worth playing around with. Or you can go for Pro, or you can maybe there's a GPU in the department that you can borrow, or you can buy your own. I bought my own, so timing is everything they say, and when I bought my GPU, it was right at the top of the bubble, where everyone was just like going crazy for mining Bitcoin. And GPUs, like you couldn't even buy them at the listed prices. And I somehow managed to get mine for $2,500. And immediately afterwards, the price crashed, and it's now available for around about $400. And that GPU has 8,700 cores. So even for something that you can buy for $400, you do get massive computational power. It's kind of frightening when you set it in motion. They're very powerful beasts at pretty reasonable prices.
Great question. So how only works with CPU and JAX works with CPU?
Yeah, good question. So the question for Zoom viewers is does number work on the GPU as well? That's a really good question. So if you use number, you can use number on the GPU. So normally the traditional way of programming GPUs is to use the C programming language and something called CUDA. And there's an interface to that through number. And it means that you're going to be controlling your GPU in a fairly low level way. Now, when I do that, and I try and parallelize my problem, and then I compare it to Google JAX, Google JAX is around about 100 times faster than what I can do. And so actually I worked with a guy who worked at NVIDIA, and I wanted to see how well he could do. He was a hardware guy, but you had to program CUDA. So I got him to program it on CUDA. And what he came up with, again, Google JAX was around about 100 times faster. So what that's telling us is that Google has taken a bunch of really, really smart engineers and paid them a lot of money to sit around and work on this for a couple of years. And what they can do is they can take your problem and look at it, or the machine's going to look at it as a whole and figure out how to parallelize it as efficiently as possible. And they are much, much better at doing that tonight. So yes, you can use number, but I would recommend using JAX. Any other questions or comments? Okay, so all of that code is available on the page that I initially showed you.
So the course repository.
Right, it's in the course repository, or you can navigate to the conf one as we did before. And you can see all of that code is there. You're welcome to play around with it. Hopefully you find it useful. And let me know if you have questions. Okay, so let me now go back to theory. Okay, so there's a bunch of applications that I'm not going to step through, but you might enjoy having a look at them. Let's go back to one of the advertised topics that I was going to talk about and squeeze it into 10 minutes. Yeah. 15. Okay. So let's just try and get a basic idea. We don't need to go through all of the nitty-gritty detail, but let's get an overview of what's going on. And then if people want to clarify things more, then they can chat to me afterwards or ask questions. So refactoring MVP, refactoring is just the name that we made up, but it's just a way of saying reorganizing. So refactoring is a word that programmers use to reorganize programs. And I thought since Richard Bellman called dynamic programming just as a kind of, that's something that he borrowed fairly randomly from programs, between sensing here and calling this refactoring on MVP. But what I mean is that we're thinking about ways to take the problem and reorganize it, to rearrange something like the Bellman equation, to reduce dimensionality, or to achieve some other gain in efficiency, or or some representation of the problem that we're going to be easier to answer. Now we did this with job search. And when we did that, we started with a Bellman equation that was something like this, and we thought about solving this for V star. But V star was a function, or a vector if you like. It's a function on finite and many possible W values. And we realized that we could reduce this to a one-dimensional problem. All we needed to do was compute the continuation value. Once I've got the continuation value, I can solve for the optimum policy. We achieved that, if you remember, by rearranging this equation. We get this much simpler equation and then solve it. So let's think about doing this in other ways, and in more general settings. Okay, so again, I'm probably the only person here that doesn't do structural estimation. So if I give the wrong labels to things or say two things, then feel free to correct me, and I won't be offended at all. But I'm taking this as a loose idea of a Bellman equation that's coming from structural estimation. And the key change that I've made to the Bellman equation that you've seen before is I've added this epsilon term. And fortunately, I'm using the same epsilon notation that John was using in his earlier talk. So these are some kind of random factors that are affecting the reward functions. So you might think of them as random components in utility that are unobserved by the econometrician. Now, as John said, we're typically going to take these guys to the IID rather than correlated. So I'm breaking the state down. Essentially, I'm breaking the state down into two parts. One is Y, which I call the endogenous state, and the other is these random shocks, which are IID with distribution. And there's our Bellman equation. So let's think about a way that we could reorganize this. And one way that we could do it is we could look, instead of looking at the value function, we could think about the expected value function. So what I'm doing here is I'm taking, fix a given V, and take this V function as a candidate value function, and I'm going to integrate it conditional on the current state in action. So some people call this the post-action expected value function. Let's call it the expected value. Now the idea here is maybe it's enough to know this function G. And maybe that's advantageous. And one way it might be advantageous, well, let's look at these guys. So we've got V and we've got G. G depends on Y and V depends on Y, so that's no change. This one depends on A, the actions, and this one depends on epsilon, the shocks. And as John mentioned, that these shocks might be high-dimensional objects. And therefore, the set of possible shocks might be very large. Whereas the set of possible actions might be small. It might be a binary choice problem on a choice search. Maybe there's 3 or 4 choices. So potentially making this switch is going to shift us down to a lower dimensional problem. And then there might be other advantages to working with G, the expected value function, instead of the value function. We know that in general, if we take a function and then we integrate it, we take expectations of it, it tends to become smoother. So it might be that G is smoother than V, and that might make our life easier as well. Okay, so question. Can we solve this problem using G instead of V? So we look at G, we stare at the definition of G, and then we go back to the Bellman equation or Bellman's equation. And I'm going to rewrite Bellman's equation in terms of G. Okay, I just use the definition of G and substitute it in the Bellman's equation. And now I want to transform this guy. Essentially what I want to do here, I want to turn this into a problem where G is the unknown and V disappears. I want to get rid of V. So how can I get rid of V? Well, I need to use the definition. Essentially, I need to take expectations of this guy. If I take expectations of this guy, I get G. That's going to become G. But if I take expectations of this side, I need to take expectations of the other side as well. So that leads me to the last equation. And this is a functional equation where G is unknown. Now I can think about solving this type of G. So all of that seems reasonable, but we still don't know, if we do in fact solve this for G, does that actually give us an optimal policy? And how do we solve this for G anyway? So what we can do is we can introduce an operator, which we'll call the expected value Bellman operator, which is going to be defined such that fixed points of this operator are exactly going to coincide with solutions to that equation that I just showed you. So we go back, I'm trying to find a G that satisfies this. That's my job now. So I introduce an operator such that fixed points of the operator are solutions to that equation. And now I study the properties of that operator, and it turns out that it's a contraction. And moreover, the fixed point, which I'll call G star, if I take that and plug that into the right-hand side of the Bellman equation in the obvious way, this is already expected value, so I don't need to take expectations, and then take the greedy policy, and we'll get an optimal policy. So this is an entirely valid approach. Okay, so what I'm saying here is nothing new. Rather than try and prove this here, I'll show you a more general way of thinking about the problem. But before we do that, let me just note this is something that John talked about as well. So there are other ways we can think about reorganizing. For example, I could introduce what's sometimes called the Q factor. And what other people call, I forget exactly what John called it, the
Specific value function.
specific value function. Whereas in reinforcement learning, they tend to call it the Q factor. So if I define the Q factor in this way for given V, and then I can think about the Bellman equation just looks like this. And I can take that Bellman equation and I can eliminate V now. How do I eliminate V? Just have to use the definition of Q. I've got this V here, I'm going to take expectations, and then I'm going to discount. And I'm doing the same thing on the other side. And then I'm going to add rewards to both sides of this. And what I end up with here is Q, and on the other side I end up something that's like that. So we're just taking Bellman equations and we're rearranging in different ways. Now, can I use this to solve for optimal policy? And the answer is again, yes. I just introduce an operator. Such that operator, this particular operator has that Q factor as a fixed point. And it turns out this is a contraction mapping. I iterate the convergence. I get the object that I end up with. And I maximize with respect to, remember, this is the whole right-hand side of the Bellman equation. And I will get an optimal policy. So all of this just works. We've taken Bellman equations, we've rearranged them in a bunch of different ways. And then we've computed their fixed points, kind of plug them back in and take an optimal policy with respect to them. And everything just works. So to give you a sense of why that's working, let's think about this. Let's think about this. I'm going to wind up in like 3 or 4 minutes. But let me just give you the picture of what's happening. Let's think about it like this. Let's introduce a couple more operators. And I know I've given you a lot of terminology, but this will be the last, I promise. Yeah, so we've got 3 operators here. E takes expectations. D takes a function and discounts it, and then adds on rewards. And M takes a function and maximizes with respect to A. So E, you can loosely think of E as taking the expectation step, D is something like discounting, and M is maximizing. Now, if you stare at the Bellman operator is exactly implementing these three steps. I take V, then I apply E, this first guy. And whatever I get out of that, I apply D to it, and I get this. And then I apply M to it. And I max it. So T, we've now decomposed T into three operators. So I can think of the action of the Bellman operator is I take a value function and I apply E and then D and then M. And that's one update. That's applying the Bellman operator once. That's a round trip from up the top here, coming around. But now I think about it, I could take a round trip from somewhere else. I could take a round trip from here. That's a loop from here. Or I could start here and I could do a circle from here on the graph. So these are my other round trips. The first one is I'm going to apply D, and then M, and then E, D, M, E. Or I could start here, and I'm going to apply M, and then E, and then D. So I have these different round trips. And we're going to call one R, and one S, and one T. T is just a Bellman operator. And if you expand those out, they're exactly the operators that we were looking at before, the expected value operator and the Q factor Bellman operator. So these different operators are just round trips from different points. And then it's easy to show that expectation is not expansive. Maximization is not expansive, it doesn't make distances bigger. And discounting contracts. So when I put these things together, for example, if I think about R is first I'm going to discount, then I'm going to max, and then I'm going to take expectations. This is Emax that John was talking about. And I apply that to two different functions. Okay, well, E doesn't expand things, and M doesn't expand things, and D discounts things. So they're all contractions. Okay, and then the whole bunch of unique fixed points. And now it's really easy to show that if we go back to the picture, if I take the fixed point of T, which is the value function, and push it over to here by E, that's the fixed point of R, the expected value function. Now, if I put it over to here, that's the fixed point of S. So if I do a round trip on these guys, I get all these different versions of the value function. All right, I better finish. So to try and conclude this, if we think about all of these decompositions in this way, I guess what this is telling us is that I find this kind of weird, right? Because when we transform these problems, we're transforming them into lower dimensions. Now, normally when you think about transforming a problem into lower dimensions, you lose information. But because I can do these round trips, I can get all of that information back. I'm not losing anything. It's not a one-way mapping. Normally, if I have a high dimensional space and I project something into a low dimensional space, I can't fully recover where it came from. I can't invert that mapping. But because these guys are round trips, given that information, I can get that information. From there, I can get that information. From there, I can get that information. Let me wind up here. So the details, so this essentially shows that all of these guys converge, and hence the optimality properties are going to be the same. And from here, we can take additional steps. And we can think about, for example, what about optimistic policy iteration? And for that, I can take, instead of maxing, I can take M to be some application of a policy. And then I get round trips using policies. Without going through all the details, I have round trips using max, but I can also do round trips using policies. And from this inherent connection between all of these objects, so I can go from one to the other, I can now implement something like optimistic policy iteration or Howard policy iteration. So then I potentially get the benefits of projecting these into lower dimensional spaces, plus the benefits of some of these algorithms, which potentially are faster as well. I went way over time. You guys are very tired, but you've done really well sticking with me. So thank you very much. And